Hello guys, welcome to my channel Maths 4747. So today I am going to discuss subspaces of any vector space. So now what is this term? Subspace. If you have some vector space V over F, or you can write like this, and if there is any subset W of V, and it also satisfies all the 8 properties of vector space, then you can say that this is subspace of V. If W is a subset of V and satisfies all the 8 properties of vector space, then we can say that W is a subspace of V. So just write down the definition first. A subset W of a vector space V over some field like F called subspace. Now there are some conditions. If W is a vector space over F with the operations of addition and scalar multiplication. Those defined on V. Only those operations which are defined on V. So for proving subspace, what we have to do, as you know that for vector space we have 8 properties. But for subspace, there is no need to prove all the 8 properties, because the properties like commutativity, associativity, and distributive with respect to scalars, all the last 4 properties, these properties are same for all vectors of V. So if it is true for each and every vector of V, that means it is true for W also, because W is a subset. Like if this is your V, then this is your W. This is a subset of V. So if the properties like this satisfies for all the elements of V, that means this is true for W also. So we are left with only 4 properties, that is vector addition, second scalar multiplication, third one additive identity, and fourth one additive inverse. Now what is vector addition? That is if there is x and y belongs to W, which implies x plus y belongs to W. This is your vector addition. Scalar multiplication is if alpha belongs to F and x belongs to W, which implies alpha x belongs to W. This is scalar multiplication. Additive identity is if x belongs to W, then x plus 0 is x. This is your additive identity. Now additive inverse, if x and y belongs to W, then x plus y is 0. Now for every x there exists some y such that this condition holds. We say that y is additive inverse of x. So these 4 properties are needed to satisfy. So now let's go with these 3 and 4. Guys, this is also same for V, and this one also obvious for V, because now let's we prove that if there is, let's we take if x belongs to W and W, let W be a subspace, and let W be a subspace. So if it is a subspace, that means it is a vector space for all the 8 properties. So there is a some 0 dash belongs to W. So what we can write, x plus 0 dash is x, and you know that if x is in W, that means x belongs to V also, because W is a subset of V. So we can write this as x plus 0 is equal to x. Now from here 1 and 2 we can say that 0 as 0 dash. So the 0 element of W is same as 0 element of V, and for additive inverse too. So now there is a theorem based on that. Let's prove that. Now just write down the statement first. Let V be a vector space and W a subset of V. Then W is a subspace of V if and only if the following conditions hold for the operations defined on V. Just write down these conditions. That is first one, 0 belongs to W. That means for a subspace there exists a 0 element in W. Now B part, additive closed with respect to addition, that is x plus y, or you can say that vector addition. X plus y belongs to W whenever x and y belongs to W. Now third one, scalar multiplication, that is Cx belongs to W when C belongs to F field and X belongs to W. So these conditions you have to satisfy. So there should be a 0 element, there should be vector addition and scalar multiplication. So for each and every part you have to satisfy these three conditions. So let's do with the proof. So this theorem is the if and only if. So first of all we have to do if part, then else part. Now let's start with if part. So if W is a subspace of V. If W is a subspace, that means W is also a vector space with respect to F. That means W satisfies all the properties of V. So if W is a vector space, that means W satisfies all the properties of vector space, which means W satisfies vector addition, scalar multiplication, additive identity, and so on. So guys, just see the statement. Vector addition is this one. That means W satisfies this. Scalar multiplication is this one. That means W satisfies this. Now we have to prove this A part, 0 belongs to W. So as you know that W satisfies this additive identity. That means there is some 0 dash belongs to W. For every x belongs to W, we can write x plus 0 dash is x. And as we know that V is a vector space. That means if x belongs to W, W is a subset of V, so we can write that x is in V. And if V is a vector space, that means there exists some 0 belongs to V such that x plus 0 is x. Now from 1 and 2, we can write 0 is 0 dash. So the additive identity is same for W and V. Is same for W and V. Now first property is also satisfied. So now we have to do else part. That means W satisfies all three properties and and you have to show that W is a subspace of B. So W satisfies all the three properties. What are that? That is x plus y belongs to W whenever xy belongs to W. Second, Cx belongs to W whenever C belongs to F and X belongs to W. Third one is 0 belongs to W. So W satisfies these three and we have to show that W is a subspace. So in order to show that W is a subspace, what we have to prove? We have to prove W is a vector space over F with respect to same operations defined on V. So we have to prove all the 8 properties. So as you know that 3 properties are already satisfied. Now there is additive inverse. Fourth one, additive inverse. For additive inverse, what we have to show? If there is x belongs to W, we have to show that there is some y in W such that x plus y is equal to 0. And you know that 0 belongs to W is already given. So just see, if x belongs to W, then by second property, which is scalar multiplication, C belongs to F means C is any scalar. So we can write C as -1, or you can take 1, 2, 3, any real number, any complex number you can take. So if in particular we take C as -1, that means if C belongs to F and X belongs to W, that means Cx belongs to W, and your C is -1, that means -1 over X belongs to W, and you know that -1x is -x. That means if x belongs to W, minus x is also belongs to W. So if we write this, then this is equal to additive identity. So for every x there exists minus x belongs to W such that this sum is equal to 0. So we can say that minus x is the additive inverse of x in W. So in the similar way we can find out each and every element's additive inverse. So we can say that in every element W has additive inverse. So our 4 properties are satisfied. Now remaining properties are same as for V, because the remaining properties like left hand side and right hand side. So these two are equal, like this, x plus y is y plus x. So this is true for all xy, and associativity like x plus y plus z, this x plus y plus z. This is for all x, y, z. So if it is true for all x, y, z in V, that means this is true for W also. That means there is no need to prove all the remaining properties. So from this we can say that W is a subspace. So from this we can say that W is a subspace of V. So now there are some examples of subspaces. As you know that there are standard examples of vector space like Rn, Pn plus 1, this is Pn plus 1, then M cross N over F. These are over F. I mean scalars from F. This is your field. Field can be real numbers, complex numbers. So, and there is a C of R. This is a set of all continuous, real valued continuous functions. So now there are some examples. Like if you have vector space, first example, if we take vector space as set of matrices over F whose order is M cross N. So V is a vector space. V consists of matrices of order M cross N, and whose entries are from F. So now let W is a, you have to prove W is a subspace. Now W consists all the symmetric matrices of M cross N. So W consists all the symmetric matrices. Symmetric matrix means A transpose is A. That means if we take transpose of any matrix and which is similar to that matrix, we can say that this is symmetric matrix. Like if your A is 1, 2, 3, 4 and or you can take this. So if this is your matrix and we take A transpose, so this is 1, 2, 2, 1 and this is same as A. We can say that A is a symmetric matrix. So W consists all the symmetric matrices. Now we have to show that W is a subspace. Now to show that W is a subspace of V. Now solution. How we prove this? W is a subspace. So you have to prove all the three conditions. That means 0 belongs to W. Guys, 0 means 0 matrix here. All the elements in this type of vector space is of matrices. So this is a big O, you can say that. So this is a 0 matrix. 0 matrix means all the entries are 0. And this is of order M cross N. So as you know that if we take 0 matrix transpose, this is same as 0 matrix. So you can say that 0 belongs to W, first condition. Now second one is vector addition. If we take two matrices A and B belongs to W. If A and B belongs to W, that means A transpose is same as A and B transpose is same as B by using given conditions. So if AB belongs to W, then what we have to prove? We have to prove vector addition, that is A plus B also belongs to W. Now for proving A plus B belongs to W, what we have to show? We have to show that A plus B is also symmetric matrix. Like this, if we take transpose, this is same as A plus B. So if we take transpose of A plus B, we can write this as this by property of transpose. And you know that from 3 and 4, A transpose is same as A and B transpose is same as B. So A plus B whole transpose is equal to A plus B, which implies A plus B is symmetric matrix. That means first condition is satisfied, vector addition. Now scalar multiplication. For scalar multiplication, what we have to show? We have to take some field element and some element from this. So what we have to show? We have to show that CA belongs to W. This is to prove. Now as you know that A belongs to W means A is symmetric matrix. This one. So in order to prove CA belongs to W, what we have to show? CA transpose is same as CA. This is scalar. So we can write this as, we can take C outside because C is multiplied with each and every entry of A. So we can take C as outside and this is this one. Now by using this fifth equation, so we can write C into A and CA transpose is same as CA, which means CA is symmetric matrix. So scalar multiplication is also valid here. So now we can say that W is a subspace. W is a subspace of V. Now there are lots of examples you can prove in this similar way, and there are some results also. There are two results. First one is any intersection of subspaces of a vector space, any intersection of subspaces of a vector space is a subspace of V. That means if we take intersection of all the subspaces of vector space, this is also a subspace. Now second one, what about union? So union of two subspaces of V is a subspace of V. यूनियन कब होगा ये? If and only if one of the subspaces contains the other. Guys, just see that in rough part. An intersection means if there is some W and W2 are the subspaces of V, then their intersection is also a subspace. But in case of union, if there is W1 and W2 are subspaces of V, then their union is a subspace if and only if one is a subset of other. So this is true if and only if this condition holds. So we discussed one example, that is prove that W is a subspace. If there is a question like check whether it is a subspace or not, so what we have to do, like this, we can discuss one more example. Example 2. The set of matrices in M cross N over R. Now field is real numbers here, having non-negative entries. Now set of matrices in M cross N having non-negative entries. So this is your W. So W is a subset of this M cross N, which contains all the matrices whose entries are non-negative. That means all the entries are positive. So you have to check whether W is a subspace or not. So in order to prove this, what we have to check, either 0 belongs to W. It is clear because non-negative entries are there. So this 0 belongs to W. Now we have to check whether vector addition or scalar multiplication are there. So if we take A belongs to W and B belongs to W and these two are non-negative, then their addition is also non-negative. So directly we can say that A plus B belongs to W. So these two properties hold. Now third one, last one, that is CA belongs to W. If A belongs to W, scalar multiplication, where C is some scalar, that is real number. So guys, you know that if A belongs to W and from real numbers you can take C as -1 also, -1, -2, -3, any negative number. And if we multiply these two, minus A belongs to W. Is it true? Not, because W consists all the matrices which have non-negative entries, and this matrix minus A has negative entries. So scalar multiplication condition is not verified here, so we can write W is not a subspace. So for not a subspace you have to check any one property. So in exams also, if you write this one only, then it is also true. There is no need to prove these two. There is no need. So this is the example of a non-subspace. So I am just stopping here. Thank you guys.